NASA's most ambitious mission yet is on the verge of liftoff. A probe, destined for Alpha Centauri, the nearest star beyond our sun. Over 25 trillion miles away. No astronauts aboard, only instruments, onboard intelligence, and years of preparation. This journey is unlike any before it. A voyage into the vast unknown, where communication with Earth will take years, and course corrections must be made independently. At its heart lies an ancient challenge: measurement. For centuries, humans have sought to understand their place in the cosmos by measuring space and time. The tools we use today stem from discoveries made over 500 years ago during the Renaissance. But can we trust these early scientific ideas to keep pace with the demands of interstellar travel? Can we trust measurements across distances so vast that they defy everyday experience? This is the story of how measurement evolved, from shadows on Earth to signals from the stars, and how it must evolve again to guide us across the infinite. Long before telescopes or rockets, humans began measuring their world and beyond. Eratosthenes, a Greek mathematician and astronomer from over 2,000 years ago, used simple sticks and shadows in two cities just to calculate Earth's circumference. His estimate was remarkably close, off by just a few percent. This wasn't just curiosity. It was the first step toward understanding the scale of our world. Centuries later, in the 1500s, Nicolaus Copernicus revolutionized our view by placing the sun at the center of the known universe, challenging millennia of Earth-centered thinking. Johannes Kepler refined this view, discovering that planets orbit in ellipses, not perfect circles, a subtle but really crucial insight. Galileo's telescope confirmed moons orbit other planets, proving that the solar system was complex, not just a static structure. Tycho Brahe's painstaking star catalogs, compiled with modern instruments, provided the detailed data Kepler needed to define his laws of planetary motion. Together, these pioneers laid the foundation of modern astronomy, turning the sky from a realm of myth into one of measurement. They showed us that with careful observation and math, we could chart the heavens in the universe. Fast forward to today. NASA's probe to Alpha Centauri must travel more than 25 trillion miles, over 1,000 times farther than Mars. But here lies a colossal problem, the tracking problem. Even the smallest errors in measuring position or direction can grow exponentially over such vast distances. Imagine aiming a bow and arrow at a target 100 feet away. Being off by 1 degree might still hit the mark, but stretch that distance to thousands of miles and a 1 degree error becomes a miss by miles. At Alpha Centauri's distance, even a tiny angular error could cause the spacecraft to drift millions of miles off course. That's a problem NASA's Deep Space Network cannot solve alone. The network communicates with spacecraft within our solar system, but signals travel at the speed of light, meaning messages to Alpha Centauri would take over 4 years to arrive. That would be another 4 years to pass before Earth would receive any reply. But then, the probe could be far off course, with no way to fix it. The problem doesn't end here. Einstein's theory of relativity revealed that space isn't flat or static. It's a dynamic fabric warped by both gravity and motion. Light bends around massive objects, and time slows or speeds up depending on gravity and velocity. This means signals in spacecraft don't travel simple, straight paths. The very fabric of space-time itself distorts measurement, complicating navigation. The tracking problem is not just about distance, it's about understanding and compensating for the universe's strange layout. How do we solve this cosmic puzzle? One answer lies in autonomy. The probe must become its own navigator, capable of making decisions and corrections without waiting for Earth's commands. Enter pulsars, the remnants of massive stars that have collapsed into neutron stars, spinning hundreds of times per second. They emit beams of radio waves like cosmic lighthouses. blinking with incredible accuracy. These pulses serve as natural galactic clocks, and by comparing the timing of pulses from multiple pulsars, the probe could determine its precise position in space. This method, called pulsar navigation, lets the probe know where it is without relying on delayed Earth signals. Inside the probe, an atomic clock, based on the vibrations of cesium or rubidium atoms, keeps time with astounding precision, accurate to a billionth of a second. This clock ensures that timing measurements from pulsars are reliable. We could couple this data with onboard artificial intelligence, which constantly analyzes sensor data, projects trajectory changes, and executes course corrections in real time. This is a dramatic leap from early days of astronomy, where humans calculated positions from Earthbound observations. Now, machines could think and steer themselves through the cosmos and universe. Autonomy is powerful, but it's not perfect. What if pulsar signals fade or onboard systems malfunction? The next step could be a galactic GPS, a vast interconnected network of satellites, stations, and probes scattered throughout space. Like the GPS system on Earth, which uses dozens of satellites to determine position, this network would allow spacecraft to continually update their location with extraordinary accuracy. Building such a network would be an enormous endeavor, requiring decades, billions of dollars, and international cooperation. But it could transform space travel from a risky venture into a reliable and even commercial enterprise. With galactic GPS, spacecraft navigating the solar system and beyond could update their coordinates in real time, no matter how far from Earth they travel. Precision isn't just important, it's essential. In 1999, NASA lost the Mars Climate Orbiter because two engineering teams used different units, one in metric and the other in imperial. This small mistake sent the spacecraft hurtling into Mars's atmosphere at the wrong angle, where it burned up. The loss cost hundreds of millions of dollars and years of work. Now, imagine a similar mistake on missions lasting decades and crossing interstellar distances. Such errors could doom a probe with no hope of rescue or repair. Measurement is the lifeline of space exploration. A single, small mistake can become catastrophic when multiplied over the void of space. Early scientists gave us the tools to measure the skies. Their discoveries changed humanity's view of the universe and opened the door to space exploration. Today, these tools evolve. Pulsar navigation, atomic clocks, AI corrections, and galactic GPS are the next steps, building on centuries of discovery. This isn't rejection of early science, it's its natural evolution. We stand on the shoulders of giants like Kepler, Galileo, and Copernicus, reaching further than we had before. Humans have always asked, where am I? From measuring shadows on Earth to mapping stars in the sky, measurement has been the key to understanding and exploration. Every journey across oceans, continents, or planets depends on knowing where you start and where you're headed. As we prepare to send probes, and one day people, to other stars, measurement remains the compass guiding us. The infinite challenges our understanding, but it also drives our curiosity. In measuring the vast unknown, we measure ourselves, our ingenuity, our determination, our dedication to science, and our hope. No matter how far we travel, every journey begins by knowing exactly where we are. From ancient sticks in the sun to atomic clocks in space, the story of measurement is the story of humanity's quest to explore and build on what we knew in the past. To explore the unknown, we must first learn how to measure it once again.